Hey guys, it's Pranay, and today we're going to be doing a momentum problem involving a non-linear collision. So as always, email questions to TutorSubmission@gmail.com for solution videos in less than 24 hours. All right, so let's get started. So the question we have here is two billiard balls of equal mass move at right angles and meet at the origin of an XY coordinate system. So ball A is moving upwards along the y-axis at 1.6 meters per second, and ball B is moving to the right along the x-axis with a speed of 4.8 meters per second. So after the collision, assumed to be elastic, and this is important, ball B is moving along the positive y-axis, as can be seen in the figure. All right, so let's go ahead and get started. So as we can see, this is a non-linear collision, right? So we're going to have to tackle this a little bit differently than we would with most momentum problems. So right away, we're going to sort of assume, so we know the direction that ball B is going in after the collision, right? But we don't know what's going on exactly with ball A. So for now, let's just kind of assume that ball A is going to go, maybe in this direction or something like that, right? It's going to go at some angle, and that's going to be we're going to call that theta, and it's going to take some trajectory. So it could go like this, it could go maybe like here, like come back this way, or it could even go straight along the x-axis. We don't know that yet. So let's try to, we're going to try to figure out the angle as well as the speeds, the final speeds of ball B and ball A. All right. So yeah, so let's go ahead and start making equations for this. So right away, one thing to note when it comes to a non-linear collision is that you have to sort of take momentum in an XY coordinate system. So in this case, it might be a little tricky because you might be wondering like, oh, how would I like have an equation that draws all of these variables together? So we can just separate this through like, an X and Y sort of system here where, starting with X, all the momentum is going to be conserved in the X direction. So in other words, if you look at the initial momentum for the X direction, it's all in ball B because ball A is moving in the Y direction. So there is no X component for the A ball initially at first. It's all in ball B. So when we're writing momentum, when we're talking about the initial momentum in the X direction, it's only going to be attributed for ball B. So we can say, mass and then B, so mass of ball B times the initial velocity for ball B. So V, and then I'll say BI for initial. And of course, just to put this here, momentum is M times V, right? And then, so this is the initial momentum in the X direction. Now, for the final momentum, this is going to be a little bit more complicated because when we go look at what's going on over here, so while there is no X direction for ball B in the final momentum, because see, it's all in the Y direction now, there is going to be a X component of momentum for ball A. I mean, we don't for sure know that because there's a chance like the ball A could be going like, continue to go in the Y direction or something. But for now, we're going to assume that there is a X component for ball A. And that's going to be, along, like based on this angle here. I'm just going to fill in these arrows here. So this arrow is going to represent the Y component of the X direction of the final momentum of ball A. So we're going to call that VAF, and then Y. And then this one, we're going to say for this component, it's going to be VAFX. And then this one is going to be, we're going to say the hypotenuse here, this is going to be VA final. And yeah. So going back to here, so the final momentum, based on like the figure that we've drawn here, is only going to involve the x component for A in this case. So we'll say MA times VAFX. Okay. So just to make things simpler, they did say that the balls are of equal mass. So from now on, I'm just gonna, I'm not gonna write B and MA anymore. I'm just gonna write M. And anyways, mass doesn't really matter for this. You're gonna see that it's not gonna matter because it ends up canceling out in like all the equations we're gonna do. So it's not gonna be that significant anyways. So we're just gonna have VBI or VB initial equals VAFX for this part. Over here, what we're gonna have is if we see on this side, initially the y component only has ball A moving here initially. So we're going to go ahead and say M times VA initial, I'm going to write that here, is equal to, and then now when we go look at the final momentum for the y sort of direction of this figure here, we'll notice that there's going to be two sort of components, because the ball B is moving in the y direction, and then there's also a y component for the final momentum of ball A. So we're going to add those together, and we're going to say, so V, B, F. So there's, sorry, I forgot an M here. So M, but that's going to cancel out anyways. Plus M times V, and then this AFY. And I'm going to cross these out, cancel these. All right, so this is what we have so far. So we know VBI, and we do know VAI. But we can kind of simplify these variables like VAFX and VAFY, because we know that they have this angle in common, and that VAF, and using trig we can rewrite them in terms of each other. So I'm gonna do that right here. So VBI equals, so VAFX can be rewritten in terms of VAF times cosine of theta. Sorry. Times cosine theta. And then on this side, so VAFY can be written in terms of sine theta times VAF. So the next step is we need another equation, because this alone, what we have, is not going to be enough to solve for what we need. We have too many unknowns. So I'm just going to go take this a step further and plug in the values that we do have here. So for this x side, we have VBI, which is going to be equal to 4.8 meters per second. But we still do not know these other two variables of VAF and theta. And then so for VAI, we know that is going to be 1.6. All right, so going back to the question, this important part that I underlined here is that the collision is elastic. So if it's elastic, that essentially is saying that the kinetic energy is conserved. from both before the collision to after the collision. Now, now if it was inelastic, that would mean that the kinetic energy is going to change, and typically it would decrease after the collision. And just to quickly do a little bit of review here, an inelastic collision typically happens when the objects collide and stick together and move, whereas in this case what's happening is that we know that these pool balls are colliding and then going off in separate directions. So that's why they're saying that the collision is going to be elastic, and therefore kinetic energy is conserved. Equation, right? So kinetic energy is half mv squared. Really quickly, it's also important to distinguish between scalar and vector quantities here. So for when it comes to momentum is considered to be a vector quantity because velocity is a vector quantity. And so when you look at the equation, P equals mv over here, when you have a vector quantity like velocity and mass is a scalar quantity, when you multiply a scalar with a vector, you end up with a vector value. So that makes sense. And then with kinetic energy, even though it does have velocity, kinetic energy is considered to be a scalar quantity because velocity is being squared here. So the negative goes away, so it would end up being scalar anyways. So with that in mind, we don't need to do we don't need to separate kinetic energy into x and y components or anything like that. We can just take it at face value and combine it all into one equation. So what that will look like is starting with the initial kinetic energy, we would have half times m. Once again, this would be ma, but we're just gonna write m for now. M times v a initial squared plus half times m times v b I squared equals half times m times v a final squared plus half m v b final squared. Okay, so right away I can cancel out the half and the m for everything. Okay, so that leaves us with just the velocities. Okay, and then we can go ahead and plug in the values that we know for these two because we have those. Okay, so now we have this equation, and I've just kind of left these values here. I didn't actually square them and add them together just because in a minute you'll see why I did that. It'll be easier to visualize the the calculation that we're gonna do. So going back up here, so these were our final equations for what we determined from the momentum side of things. And so as we can see, everything is so we have three variables, right? We have AF, VAF, and then VBF and theta, right? So we have three variables and two equations. So we still do sort of have a problem, and we're gonna have to figure out which variable that needs to go away. So one thing that we can sort of do is try and plug these two equations that we have into this equation and see if anything cancels out or something, if there's another piece of information that we can gain from this. I'm gonna go ahead and just isolate VAF on this side so that we can plug it in over here. And then same thing on this side. So 1.6 minus VAF. Okay, So yeah, it looks about right to me. So now going back here to substitute these values. So keep this the same, sort of condense it a little bit. So VAF, we have 4.8 over cosine theta squared. So for this one, I'm gonna have to take this just like a step further because I still have VAF in this equation. So I'm gonna actually use this expression for VAF, just put that into there. So VBF equals 1.6 minus 4.8 times sine theta over cosine theta. Then I'm going to finally plug that in over here. 1.6 minus 4.8 sine theta over cosine theta squared. All right, so here now we finally have a final equation here where we have everything in terms of theta, right? But this equation is pretty messy, and it would be pretty complicated to try and solve this out using algebra. So let's do ourselves a favor and just take a look at it and try to maybe plug in some values and see like what's going on here, right? So if we just take this sort of approach where we look at these parentheses individually, we'll see that, okay, so here, isolated, we have this 4.8 over cosine theta. Now, if we just plug in 0, like simply 0 for cosine theta, cosine of 0 is 1. So this would give us 4.8 over 1, which is 4.8. And then 4.8 squared is, that's the equivalent of the 4.8 squared on this side. And likewise, if we go over here, we plug in 0 for cosine theta, that gives us 1. And then if you plug in 0 for sine theta, that's 0. So this whole expression goes away, even though it's a 1 on the bottom. And we're left with 1.6 minus 0, which is 1.6. And this is great because now we're left with exactly the same expressions as whatever is on the left side here. It's the same thing, 4.8 squared plus 1.6 squared. So this basically tells us that theta is 0. The angle is 0 degrees. So that was, not only does that simplify a lot of things for us here, but what that basically implies or suggests is that if this angle is 0, then there's no like triangle here, there's no angle, and basically ball A collides with ball B and then instead now goes along the x-axis in the positive direction. That's basically what's going on here. And if we go back to the equations here, what we're going to see is that essentially the final velocity of ball A is just going to be equal to the initial velocity of ball B. So these velocities just flip-flop essentially. And yeah, so we can see that over here because in this equation we see VBI, or initial velocity of ball B is equal to the final velocity of ball A. And we can ignore this cosine theta because cosine of 0 is 1. So that is not really part of the equation now. So now, what we're left with is VAF equals, 4.8 meters per second. And VBF is equal to, same thing on this side where VAI is equal to VBF plus VAF sine theta. And remember, so this goes to, sine of 0 is 0, so this expression goes to 0. And VAI is equal to VBF, and VAI is 1.6, so therefore the final velocity of B is 1.6. So you might be wondering why we went through this whole complicated process to find the angle, plug in an equation here, this, that. And so it's also important to obviously understand the reasoning as to why we would be able to just assume that this theta angle is 0 in this case. But also the work that we did here would still apply if ball B was going at an angle in the like after the collision, and this would in turn cause A to also be going at an angle most likely, and yes, we would need to do trig in that case. But yeah, so in this problem we didn't end up needing to actually do that just because we got a little lucky here where ball B ended up going in the positive y direction, and theta was 0 as a result. So yeah, let me know if you have any questions in the comments. Hope you found this helpful. If you did, leave a like and subscribe for similar videos. Thank you.